Perfect. So my name is Daniel Smith. I was a software scientist at MolSSI for a while. And so I'd like to talk a little bit more about the QCArchive software stack and how it integrates with all the items that Lori was discussing and how we're going to basically go from a setting where, Psi4 uses a single node to how do we use hundreds or thousands of nodes concurrently to tackle very large problems in machine learning or crystal structure prediction, or even other ideas. Um, so let me see if I can share my screen here. Um, Great. Can you see my screen?
Yes, looks perfect.
Wonderful. Yeah, so as I said, we're going to do a little bit of a QC archive overview. And so, QC archive is a multi project, so it's not specific to Psi4, but it is certainly much enabled by Psi4. Psi4 is one of the primary compute engines and likely adheres closest to the overall architecture design of QC archive. Everything that I'll talk about here, we primarily go through the QC Engine interface that Lori was discussing. So you can either use Site4, you can use programs like Games or NWChem, or Torchani or OpenMM, or just a huge numbers of programs with the software stack. But we'll try to, because of Site4 discussion, we'll try to keep it specific to this particular program. And so, I thought always the best way to start with these is going over, the extremely high level details and goals of the stack. And really, what QC Archive is fundamentally is about the computation organization of large scale data. I think certainly, when I was in grad school, we ran, computations by the hundreds, and that was really cool. And now, as time went on, we started running by thousands to tens of thousands. And now for majority machine learning, you need to run, computations in the tens of millions. And so, our canonical way of looking at, how do we hold and store data at the scale, I think doesn't really quite hold up. And so QC Archive is really an ecosystem that takes this stab at saying, how do I really manage and harness quantum chemistry evaluations at scale? How do I run these things? How do I share these kinds of items? So fundamentally, that's really what we're after. So for today, though, we're going to talk through just a couple of use cases. So use case one is going to be generation and storage of machine learning data sets using the PC archive stack. Use case two is going to be going through benchmarking. So, how do I take, my standard S22 benchmark set? How do I automatically run a whole bunch of methods against them to evaluate their performance? And then finally, it's going to talk about the really aspirational goal of PUC Archive, which is how do we use all this data and all these tools to actually inform day-to-day molecular analysis and design, which is really where we'd like this platform to head over time. And then the final bit is, of course, because it's a multi-project, this entire software ecosource is completely open source. It is guided by the community itself. So, we'll talk a little bit about how we engage and the partners that we engage in there. So Laurie's talked a little bit about, the elemental and engine layers of QC Fractal. So I thought I'd broaden this up very quickly to give a much higher level overview of how all of these ecosystems interact. And so primarily we have a couple pieces. And so it looks like I do not have a mouse, but if I look in the bottom right corner, you see where QC Engine lives. So all of QC Engine and QC Elemental really lives purely in the compute piece of this ecosystem. Other pieces involved are, QC Fractal in the center is the database that holds all the results, it holds all the new tasks to compute. And what that central database is that can be interacted from a user perspective. So I can be sitting on a laptop, I have a Fractal server somewhere in the cloud, I say, hey, Fractal server, run these, 100,000 calculations for me. That Fractal server will pick these items up, and then it'll start shipping it off to any kind of supercomputer or local cluster that you have attached to that Fractal instance. So on top of, this abstraction of saying, let's use many different cores at like a single compute location, Fractal is also capable of using it at many compute locations simultaneously. A really good example of this is MolSSI does have a central Fractal server, and what this does is this runs at anywhere between a dozen and 2 dozen physical locations and academic campuses for a variety of open source projects all at the same time. So we're able to, dump task definitions or quantum chemistry compute centrally and automatically farm these out to whoever is willing to provide compute for the central server. Narrowing it down just very slightly to give you an idea about compute. So I think, very used to, we're used to this idea of, I'm going to build an input file, I'm going to like SSH in my compute cluster, I'm going to build like a Slurm script, and then it's going to run, then I'm going to like run a parsing script on that, and then finally pulling that data back to say my laptop or something like this. And so Fractal, it uses existing tools to help remove this particular bottleneck. So I like to view it as kind of like a question-oriented design of not, I want to run these 1,000 calculations, let me form all these input files, yada, yada, run them. But can I just say, hey, Fractal, run these, 1,000 tasks. And the way that works is I have these daemons on my local computing cluster, and these daemons can be these programs such as Parcel. And what they'll do is automatically spin up worker nodes, under the allocations that you have on these supercomputing resources. Take your quantum chemistry job, put it on a node, evaluate it, and ship it back automatically to the database. So the whole idea here is you really abstract away this idea of submitting batch jobs and the like. Everything can be handled through you through modern software practices and effectively distributed computing at extremely large scales. And this is just showing that depending on the supercomputer resource that you have between local clusters or cloud or campus clusters, you might actually use different tools underneath the hood. And Fractal is able to abstract all these different choices away from you, so you're simply able to focus on, I have some NERSC allocation, I'd like to use that, rather than these individual questions of like, how do I use batch on these different supercomputers. So the distributed compute hooks into this central location, and from this we're able to really imagine compute in an automated way at completely different scales. So to give you a simplified idea is we can think about a machine learning workflow, like a very, very canonical one, which is, I have anywhere from, 1 million to 10 million molecules, and I'd like to build a homogeneous data set for them. So instead of, again, going through this laborious process of SSHing into all these nodes and computing and watching them, the Fractal ecosystem is designed to handle that for you. Here's an example of an idea of what we say is computing a data set. So when I compute a data set, what I would do is I would take my, I don't know, QM3 is really small, so I take my 4,000 molecules or whatnot, and I put them into a data set. And when I would do that is I would save this data set called QM3 to the Fractal server. And then what that would allow me to do is any person who has access to that Fractal server, you're able to just simply request that data through a Jupyter interface. So all your data is stored remotely in this nice format. And then what we can do after that is we can automate the compute away. So here is an example underneath this generate energies and properties with QCArchive, where what I do is I get this QM3 data set, have it locally, and what I'm able to say is simply, hey, go compute Omega B97X with the 61 GD basis set using Psi4. And so what this would do is this would automatically loop through all the molecules in the QM3 data set, submit them to the Fractal server. These things would wait until they had capacity on a supercomputer, they'd be evaluated, come back to the Fractal server, all completely automatically for you. And again, I love the Psi4 example, but just to give you an idea of the breadth of the ecosystem, you could also say, hey, go compute Torch Annie. So this Torch Annie is a implementation of the Annie method by Adrian Roper and co. And so we're able to just go ahead and automatically submit these computations. And again, they will go off to your server, they'll be evaluated automatically, and they'll come back to you. And as an example of like how they would come back, in the bottom right-hand corner, you would just say qm3.query, whatever parameters that you'd want. And what you'd immediately get is tabular data for your machine learning methods. So, and I'm using machine learning just as an example, but if you want to do, methodology comparisons or other items, it's really quite straightforward because you just have a pandas data frame. Once you have a pandas data frame with this tabulated data, you can do any possible operation that you want with it. And what I think is also really nice about the stack is, it's not limited to this, but at least we provide, some limited tools to doing very quick analysis. As an example, so analysis on the researcher in the bottom left, if I want these violin plots, these data sets, they know like what a benchmark column is, they know, about different methods and how to do different groupings. And so you're basically able to say, hey, give me this violin plot, everything's labeled for you, I can do a conversion between a heart rate and kickoff the mole. So it provides, hooks to giving you very, very fast analysis of saying, hey, did my machine learning model do well? Should I retrain it? Do I have outlier detection? Once I have this, very highly structured data, we hope that we give a nice platform for the machine learning researcher to build on top of. And so, once we've gotten to this point, so this involves, generation of data and analysis of data. One thing the researcher is going to do is publish a paper after this. Well, we can't help too much with that one because that's not a software related problem. But when it comes to publishing a model and publishing a data, these are also two items that the QCArchive stack can help with. And I'll talk about how we integrate with those a little bit later on. But this hopefully gives you an idea, of a potential flow that this tool is really useful for. And to give you a little bit better idea is we're really, MolSSI is really looking at, supporting the machine learning community. And so there's been a lot of work in the past year to do performance improvements. So for example, data set sizes of 1 million plus are now much faster, much easier to work with because there's a lot of data. We have automated exports to HDF5 formats, so you can plug them right into kind of traditional machine learning tools. We also have plenty of tutorials and examples up on our website of doing, some C mapping and a couple other machine learning tasks. So, the website is right on the above. So QCArchive.folsi.org is going to be the portal to all of this content if you're interested in learning more. Two other things that we're really looking at as well is, making the private server setup really easy. So as I mentioned, MolSSI has this big open source server, but you can always spin up your own server if you want. There's going to be plenty of cases where, you have private data, you don't want to share it automatically by default. So spinning up a fractal, behind your own firewalls is certainly, a very canonical task, and something that we'd encourage. And also the thing that's really great about this is MolSSI has this giant database of machine learning data sets. So if you do everything behind your firewall, with your own QC fractal instance, uploading to MolSSI servers so the rest of the community can interact with this should be a very, very straightforward process. A request that we get a lot is storing wave function data. At the moment, we just store lots of, energies and gradients and Hessians. It looks like this functionality has actually been added. So, if you want to be able to store, densities or orbitals, QC Fractal now supports this kind of operation. Yeah, and so the other thing that we're always doing is we're adding, new databases all the time. It's really amazing. You can just go to the QCArchive website and watch new computations come in. I think like a couple of weeks ago we were at 30 million, now we're at 33 million. So you can actually kind of like watch them live as we expand these items. And the other thing is we can always add new machine learning models. So QC Engine's an open source software stack. If you have implementations of machine learning that you'd like to integrate with this, there's these nice templates that, particularly Lori and a huge number of other people have worked on so that we can just add new capability to the software stack through this particular abstraction layer, making it very easy to say compute entirely new columns of QM3 or other machine learning data sets for additional comparison. So lots of ways to get involved and lots of enhancements going on right now. I wanted to call out, and as an example, is Open Forcefield. So you may or may not know it, but Open Forcefield is a hybrid academic commercial consortium whose goal is to build and improve force fields. Especially for the Psi4 community, I think this is really important because Open Forcefield runs Psi4 on the scale of tens of millions. And actually, I apologize. These computed numbers are close to 8 months old at this point. I haven't updated my slide since then, and I missed that. And these numbers are just incredibly more. So Open Forcefield is one of the giant contributors to QCArchive, and they use tons and tons of Psi4 for that particular operation. They're all about open source. They've been contributing back to a lot of the code bases as well. So if you haven't seen them or haven't touched base with them, I really highly suggest that you look them up and do any kind of chatting or help that you can give them because they're a really great community. And as an example is we don't just do energies with Open Forcefield. They do lots of things like Hessians. We optimize things like large sections of open source databases like Kimball to provide these kinds of values for them. They do a lot of grid optimizations for improper torsions, for example, so like nitrogen inversion centers. And they run tons and tons of these torsion drive calculations, going around various rotable bonds to fit, their dihedral force field parameters too. So the open force field has driven a lot of kind of unique capability in terms of, these large scale workflows, within the Fractal ecosystem. And just to touch on that very, very briefly, like a torsion drive is an item where you have a single molecule, you rotate it by a little bit, you re-optimize, and you have to, from that previous geometry, rotate it by a little bit more. And so Fractal is actually capable of driving these very complex iterative workflows where I have a central scheduler, which actually does the iterations themselves, and I'm able to continuously fan out these calculations. And when I say fan out, each individual torsion drive may require, a couple hundred geometry optimizations. So it can run all those in parallel, and it can run many of these workflows in parallel as well. And so this allows Open Forcefield to basically say, hey, I'd like these torsions, go run them on, n,000 cores to complete them as fast as possible. So again, really, really amazing group there to work with, especially Psi4 and QCArchive. I believe Lori touched on QC Engine. I just wanted to give you a little bit more of an idea of the flexibility there. As an example, we were using Psi4 and doing energy computations. Another thing that we can do is we can start mixing and matching. So here's a good example of where we mix and match. And what's going on is I'm basically doing a QC engine computation using geometric as the driver. So geometric is a standalone geometry optimizer that can take in arbitrary energies and gradients and propagate that optimization for you. And in this particular case, what I'm doing is I'm using Psi4 as the backend, so we can get Psi4 based computations there. One tricky thing about geometry optimizers is that previously I'd have a geometry optimizer in all these different programs. And so getting like a true apples to apples comparison of different methods was very difficult because we didn't have a common way of saying this is the exact same optimizer across the board. With this kind of capability, we have that because, so for example, if I want to do, Psi4 gradients versus anti-gradients, I can now do that. It's wonderful for comparing machine learning algorithms. Or I can even go a little bit farther afield and say, I'd like to do something really fast. I'm going to use OpenMM with the Smirnov force field. So this is something that works out of the box today. And what this allows me to do is compose higher and higher level workflows where the actual gradient itself can be anything. So we can get these really nice and absolutely fair comparisons where we can kind of break apart, let's compare optimizers, let's compare energy and gradient methods, and then let's compare workflows. And we can do all of that on completely level playing fields with this kind of abstracting technology. It looks like I have one more general improvement slide. So this is actually kind of a fun story of handling data at scale. When we have QCArchive, like I said, it has like 30 million plus calculations in it. So one thing that will happen is that, it'll go down. Handling those backups was an interesting strategy that I think shows that, you can actually build like a lot of trust in, this QCArchive as a central location. We actually had our first drive failure and restore late last year. And we were able to, basically, not lose any data and then come back up, with a more robust solution within about 20 hours. And so that was a pretty long period of time. All the next generation items will be much shorter in terms of downtime, but I think it's kind of an interesting story of how you have all the science and then, what happens about the DevOps. So usually, like if I delete a file, it's just gone. One thing that's nice about QC Fractal ecosystem is, we have this ability to do backups and snapshots in a somewhat automated process so that you don't lose your data. Or if you accidentally corrupt your data, you can always go back and look at the snapshot. So I think that's a really important story of data integrity. On the general enhancement side, lots of logging, administrator dashboards are coming up. Our role-based access controls for, who can compute versus who can read data are coming along. And, one thing I think I should really highlight here is that the number of pull requests by the community is incredible. So lots and lots of community activity on QC Engine and QC Elemental. And so you can kind of see Psi4 is able to gain, an even broader ecosystem of users by building on top of these engine and elemental tools. Because these engine elemental tools go into additional ecosystems, kind of tying everyone together. So this is something that I really like to see. The last point that I didn't get a chance to touch on real quick is, the really hard problem of how do we use a framework like this to inform day-to-day molecular design and analysis. So I wouldn't say this is like quite the final solution, but during my time at MolSSI, I think these are two important items that we hit on. So QCArchive powers the machine learning dataset effort at MolSSI. You can find, on top of all of our computed data, at about 30 million these days, we also have curated data from data sets. So these are things like, QM9, BT, all of the machine learning data sets have been pulled underneath a single roof. Their data schemas have been homogenized. And so you can just go up there and start pulling these data sets at this point. And what I like about this is before, you'd have to go to, group one and get their data set, and group two get their data set, and you have to like kind of, munge this into a common data format. Well, you no longer have to do that. All that's been done for you. And we hope that this is a repository of machine learning data in the future. So highly encourage you to go ahead and upload your data when you can to this database to keep growing that ecosystem of this common format for machine learning and quantum chemistry. Another thing that I mentioned is the ability to get quick comparisons of data. So how does method one do versus method two? And so this is another web app that we have, and canonically the QCArchive database has all of your standard benchmark sets. So all the S22s, all the GMTK55s, et cetera, all underneath one roof. And so MolSSI has undergone a project where we started doing an enumeration of different methodologies with different basis sets, so that we could basically build a tool like this, where you can just go to this website above. You can choose your data set, you can choose your method display and your basis sets, and you'll be able to very quickly say, how does method X do versus Y? How does basis set 1 versus basis set 2 do? So this is, again, a web app that's up that's right now. I encourage you, if you're interested in what methodology to use, to go ahead and pull through that. And the one thing I should mention, especially for this community, is all this data is actually Psi4. So every single method and basis set on these is Psi4 computations. So this is about 1 million computations in total, which isn't that much, but kind of like enumerating the space is a bit unique in terms of evaluations, I think. So finally, to recap, QCArchive is really about pulling, a large community together. So Psi4 is a huge part of it, but there's also many different codes and ideas which have, contributed from very large community. What's nice about this is not only, do we have this community that we're building on top of, we're kind of like in the middle, where now we have other tools that are building on top of the QCArchive ecosystem. So, you saw Psi4 doing distributed computing and the like, and so it's just one example of this. And, the idea here is the more people that we can work on this common abstraction layer, the more powerful it's going to be for everyone. So we kind of fit right here in the middle of that. We work a lot with cyber infrastructure and NSF division on distributed compute. We have this ability to do private databases. We have all kinds of multi-communities as well coming into play in terms of their data sets. So actually, the Shell group contributed a lot of the standard benchmark sets to the QC archive. We have a reaction data set group called PACM who's contributing. We have some newer dataset groups also adding some of the more modern and cutting edge data sets as well. So it's kind of like this growing community where if you have a data set that you want in the open, you can always add it to this QC archive cluster. Finally, we use lots of visualization software. So, Jupyter, is like a first-class citizen to interact with this data using Plotly and Pandas and the like. And then finally, like I said, we start interacting with these gateways portals. So, we gave a couple examples in the past two slides what gateways looks like for QC Archive, but we hope to interact with these other communities a lot more as QC Archive to kind of enhance this particular, full, iteration from CMS community to final end. Last thing I want to say, because I see David looking at me, is tons of downloads, releases, computations, etc. Go there to find that data. And also, I can't imagine the massive list of people, and this is incomplete, who have helped on this project. So really, thank you to so many people for making this a reality.